In this video, we're going to prove the component method of the dot product. So we know that the component method of the dot product tells us that if we have two vectors in 3 dimensions, a and b as written here, then a dot b will be a1 b1 plus a2 b2 plus a3 b3. In other words, multiply the x's, multiply the y's, multiply the z's, add them together. Well, to prove that, let's draw a graph. Let's imagine we have the vectors a and b as shown. And what we're going to do next is we're going to put the third side of that triangle, so to speak, and we're going to evaluate that third side's length, quantity squared, two different ways. One way we're going to do it is to imagine that third side is the vector AB. And then we're going to think of AB as being B1 minus A1, because remember, A is just a point, A1, A2, A3, and B is just a point, B1, B2, B3. The vector A has those components, and the vector B has those components. But going from point A to point B will be as simple as subtracting backwards, as we've discussed earlier. B1 minus A1 will be the x component of that vector. B2 minus A2 will be the y component of that vector. And B3 minus A3 will be the z component of that vector. And then we'll be able to determine that the length of that vector, the magnitude, which I'm showing as small d, will be equal to the square root of b1 minus a1 quantity squared plus b2 minus a2 quantity squared plus b3 minus a3 quantity squared. So that would mean that to square d, squaring it would give me the same expression but without the square root over top. And we would just simply have to expand them all out. Using some fairly simple grade 9 ideas, b1 times b1 will be b1 quantity squared, b1 times negative a1, and negative a1 times b1, collecting those like terms, we'll get minus 2a1 b1, and then negative a1 times negative a1 would be positive a1 squared. A similar process used for the other ones would give you the expression as written at the bottom. So that'll be one of our expressions for d squared. Now, another way to determine the value for d squared would be to use the cosine law. Well, the cosine law tells us that d squared will be this magnitude squared, the vector OA's magnitude quantity squared, plus the vector OB's magnitude quantity squared, minus 2 times the magnitude of vector OA times the magnitude of vector OB times the cosine of the angle in between them. And that's what we've written out. Well, we know the magnitude of OA, the magnitude of the vector OA will be the square root of a1 squared plus a2 squared plus a3 squared. And the magnitude of the vector OB will be the square root of b1 squared plus b2 squared plus b3 squared. So the formula calls for the magnitude of OA quantity squared, though, so we can just get rid of that square root. And the magnitude of OA quantity squared is a1 squared plus a2 squared plus a3 squared. And similarly, the magnitude of OB quantity squared is b1 squared plus b2 squared plus b3 squared. So putting all that together, we get this expression plus this expression, as stated earlier, minus 2 times this expression right here, times the cos of theta. Now, setting d squared from the first method a couple slides ago equal to d squared from this method shown above gives us that b1 squared minus 2a1 b1 plus a1 squared plus b2 squared minus 2a2 b2 plus a2 squared plus b3 squared minus 2a3 b3 plus a3 squared is equal to this expression, which is a1 squared plus a2 squared plus a3 squared plus b1 squared plus b2 squared plus b3 squared minus 2 times the square root of a1 squared plus a2 squared plus a3 squared times the square root of b1 squared plus b2 squared plus b3 squared times the cos of theta. Now, just notice something before we go too much farther. A1 squared here and A1 squared here, they cancel out. They're on opposite sides of an equal sign. There's an equal sign right there. A2 squared and A2 squared, they cancel out. A3 squared and A3 squared, they cancel out. B3 squared and B3 squared, B2 squared, B2 squared, B1 squared, B1 squared. They all cancel out. So on the left-hand side, we're just left with negative 2A1B1 minus 2A2B2 minus 2A3B3. And on the right-hand side, we're left with that expression down at the bottom, as shown. Now we're going to factor negative 2 out from this left-hand side. And when we do that, we get this expression. And we already have it factored out from the right-hand side, so that's fine. Dividing both sides by negative 2 gives us this right here. Now, think about it. What does the square root of A1 squared plus A2 squared plus A3 squared equal? What it equals is the magnitude of the vector A. And what does the magnitude of b1 squared plus b2 squared plus b3 squared equals? So when you think about it, it equals the magnitude of the vector b. And cos theta remains cos theta. And so what we have is that this expression on the left is actually equal to the magnitude of A, magnitude of B, cos theta. Well, that is A dot B. So what we have is that this expression, this very convenient component method form of multiplying x's, multiplying y's, multiplying z's, and adding them, is actually equal to A dot B. And that's what we've written down here. A1B1 plus A2B2 plus A3B3 equals A dot B. And so the proof is actually not too complicated for such an amazing and useful theorem that really makes a lot of our work easier and allows us to do some wonderful things.